We're going to discuss light scatter and what it means in flow cytometry. There are many aspects to light scatter, and several terms we use are related to light scatter properties. For example, you might hear terms like size, shape, granularity, complexity, birefringence, and refractive index, all of which are related to light scatter. First, let's talk about forward angle scatter, which is also called narrow angle or falls, F-A-L-S. We mostly collect this at about 3 degrees angle off the laser beam. Falls signal strength is very large. It can be 100,000 to 1 million times the intensity of the fluorescence signal. Our knowledge of light scatter is heavily derived from the work of Gustav Mie, who developed Mie theory in 1908 as a mathematical physical theory of the scattering of electromagnetic radiation by spherical particles from about 1/10 the wavelength of light to several microns. If you look at the diagram I just drew, you'll see that there is a strong interaction between the light source and the particles illuminated. Mie theory operates from around about 10 nanometers to about 10,000 nanometers or 10 micron spheres. In fact, when you send a particle through a flow cytometer, you collect a histogram that reflects the strength of the forward scatter signal. Noise might look like this, and a strong signal like this. And of course, this might be the sort of histogram you get when you run a single size calibration bead. At the same time, you can of course collect a fluorescence signal coming from those same beads, and a histogram of that might look like this. You would not be surprised to learn that we often use light scatter to trigger sample collection. More about that in another Cytorial. Many people say that forward angle scatter measures size, but that's not quite correct. In fact, it's only correct for a small range of perfect spheres, as I just mentioned. So when you look at this diagram of how we measure falls, you can see that the intensity of the signal is dependent on the angle of the forward detector. In this cartoon, I made the 3-degree signal smaller than the 4-degree signal just to show you how the angle can make a big difference in the signal intensity. In fact, different instruments have different angles of light scatter, and that is why they don't all measure particles the same way. This means you often can't compare scatter plots from one brand of instruments to another. Let's talk about side scatter for a while. We've seen several names for side scatter. One is orthogonal scatter, another 90-degree light scatter, and sometimes people even speak about wide angle scatter. Now, if we follow this diagram, which is similar to the earlier one, you see that the light measured for side scatter is going in the same pathway as fluorescence, which is at 90-degree angle from the laser beam. The difference between this scatter and the fluorescence scatter is that the side scatter signal is the same wavelength as the laser beam, and that is why you have to block this light after the side scatter detector. If you don't, you'd overload the fluorescence detectors with a ton of laser light. We can say that the major impact on side scatter signal is the granularity or complexity of a cell. Neutrophils and eosinophils have a lot of granularity, so they produce a large 90-degree light scatter signal. But latex beads and lymphocytes have little to no structural complexity, so they have a very low side scatter signal. You can see that in this diagram where I've shown you exactly what type of cells produce large and small side scatter signals. Note that we very often gate out red blood cells and debris in the bottom left corner of the dot plot. This is often achieved by settings on the flow cytometer to reduce its sensitivity to small particles. So, in summary, here are our findings on light scatter. For forward scatter, also called falls and narrow angle scatter, we've identified a complex relationship between size and scatter, with the caveat that non-spherical cells should not be considered linear with respect to forward angle scatter. Since the signal is strong, we can measure it with a low-cost diode, and we mostly try to measure falls at about 2 to 3 degrees. Regarding side scatter, that is usually measured at 90 degrees to the laser beam. That is also called orthogonal scatter or wide angle scatter. It is a measure of the granularity and complexity combined with forward angle scatter can be very useful in differentiating several different cell populations.